Okay, good morning, good afternoon, and good evening, everyone. My name is Nando Ochoa. I'm a professor of smart grids and power systems at the University of Melbourne in Australia, and also professor of power smart grids at the University of Manchester in the UK. This particular keynote is about electric vehicles and the electric grid. I understand this is not a power engineering conference, but the idea here is to give you a little bit of some of the challenges that the grid, the power grid, is seeing and will certainly continue to see in the years to come as people adopt electric vehicle technology. Before I start, I just would like to thank the organizing committee of the Vehicular Power and Propulsion Conference 2020, and in particular, the organizing committee from the University of Oviedo in Spain, and Paula Rodey in particular. Thanks for the kind invitation to deliver this keynote. Okay, so we have approximately 40 minutes to go through this, so let's start. So first, I will sort of try to present the basics here. Again, I understand that my audience, so I will be very high level, but at the same time, just to give you a little bit more of quantitative nature of the potential challenges that I was mentioning, I will present two case studies. One is related to a large scale trial that we did a few years ago in the UK called My Electric Avenue. I will present some of the interesting results, findings, and some key remarks as well about that project, which was all about managing the charging point of the electric vehicle. This is in particular very close, well, the electric vehicle managed by used by end consumers at home. But then I will also add some a few slides about charging stations, in particular fast charging stations, and the challenges that they bring as well, and how we have to look at a future where cities with these technologies, they have to look at how to do this holistically rather than just deploying fast charging stations wherever, and then creating certain impacts on the power grid as well. So let's start. All right, what are those impacts I'm talking about? Let's start with the basics. So when we design our residential areas, those streets, some of you might see those poles with the wires, typically overhead lines, if you don't live in the city center necessarily, and then you connect from those wires one of the faces to your house, and we design those areas, those poles, those wires, you know, what we call the electric network, particularly at the low voltage levels, those voltage levels that we connect our houses to, in such a way that it is just to deal with the peak demand, all right? And at that moment in time, of course, we manage them in such a way that we expect kind of a coincidence, you know, for the houses during the peak, like let's suppose at 8 p.m., you know, during a summer day or winter day, depending on the part of the world that you are. And well, all the currents and all the voltages are going to be within limits for that worst case scenario. Now, the problem is that the moment that you have electric vehicles connected to a circuit, you know, part of the grid that hasn't been designed to have electric vehicles, then of course what you have is an increase of load. It's like in your house when you actually start, you know, putting much more loads to power outlets, you know, that they were meant to have. Of course, your fuses are going to blow up. Same thing here. We have fuses as well, actually, as a matter of fact, here, and that's an issue. And not just that the currents, you know, that will trigger the fuses, but we will have as well some voltage drops. And voltage is something that we want all our appliances to have within certain limits, and those limits depend on the part of the world that you are in. Now, this is not just for residential areas. The moment that many parts, you know, many neighborhoods start having electric vehicles and charging when they come back from work at home and have this simultaneous kind of charge, then of course, you know, the impacts are not just for that little neighborhood, but across our electricity network. This is what we call the medium voltages, the higher levels, so the bigger poles, bigger pylons, and so on. And this is a challenge. So the more we see electric vehicles, the more we're going to see some challenges. The question is how to best manage, how to best mitigate those problems. So there are different solutions, of course. It's more demand, and the challenges of more demand is nothing new to the companies that manage the poles and wires. But of course, there's a cost to it. You can actually, to manage voltages, you can do things with what we call the offload changes. I'm not going to go into the details. We can put bigger transformers, bigger wires, as you would do in a house. You know that you create an upgrade because of a new room. So you would put new wires, a new switchboard, for instance. So same principle, really, because it's more load, all right? But also you can think of, well, I mean, is it really worth it to have all these new transformers, all these new copper assets? What about if we start managing the charging points, you know, just at certain times, not charging everyone simultaneously? And then the question really is about what is the most cost-effective solution, right? So when we talk about management of electric vehicle charging points, what we are saying really is that at the moment where, you know, we have this problem, you know, let me just get my laser point here, with all the vehicles charging simultaneously without any control. Well, I mean, let's just use a little bit of intelligence and disconnect some of the charging points just for an hour or two, or whatever it is needed according to the corresponding management system. It can be very close to your house or much more centralized in the cloud, whatever it is, in a way that, you know, the load is not that big. And then, of course, when there's a space in the network, electrical space, let's say, then you just reconnect those vehicles. So that's the idea. Disconnect when needed. Now, this can be done with prices, of course. This can be done with many things. The charging level is not just disconnecting the charging point. There are different things that can be done, right? Now, let's look at the other aspect of the challenges. The moment that you see more and more electric vehicles, not just, you know, the networks connecting, you know, those cars, you know, at home, but also the moment that we start seeing fast charging stations, which is the equivalent of petrol stations, right? So these are really massive stations. And well, I mean, when we look at this, yeah, we cannot look at charging stations, fast charging stations that are going to be next to our houses. They are going to be similar to petrol stations, not necessarily next door, but, you know, in certain neighborhoods across the city. And perhaps, you know, the moment that we have a few, there's not going to be a significant issue in terms of, you know, the electrical network, you know. But the moment that we have more, then we need to think carefully. Also, at the same time, this is talking about infrastructure, the electricity infrastructure, but also what about the traffic flows, you know? Are we gonna push all these electric vehicles to go to certain areas just because of the fast charging stations that are there? So how do we affect flows, vehicle flows, you know, because of the fast charging station locations as well? So how do we allocate fast charging stations cost effectively is another question. So there are interesting challenges here to address, and I will try in the next 30 minutes or so to address these questions with some case studies. So let's start with the electric vehicle charging point management. So this is some slides that are the results, the findings of a project called My Electric Avenue, as I mentioned earlier. This was, at the time, the largest electric vehicle trial in the world. And it wasn't just about extracting the information of how people charge the electric vehicles. Quite interesting, it was about trialing as well a technology that was actually disconnecting the electric vehicles at certain moments in time to help the grid, as I was explaining in my earlier slides. More information and reports are publicly available through these two websites that I'm going to provide as well the PDF of this slide. So the context at the time, these figures already are a little bit old, so apologies for that. But the trends in the UK are such that, well, there's an expectation of many electric vehicles in the next years. Today, including hybrids, we have in the UK a 250,000. Now, sounds like a lot. But that's not even 1% of the entire fleet, which I think is almost 40 million cars. I'm not really sure where it's just cars or it's all type of vehicles, but still it's quite a large number. That doesn't necessarily mean that that's bad, because that means that in terms of the trends that they were expecting a few years ago, well, I mean, they are even higher than the high uptake scenarios. Now, and the challenge here is not because we have only not even 1% of the fleet of cars, is that you have clusters. Technology sometimes goes into clusters. Certain neighborhoods or more often neighborhoods will start having more electric vehicles, and then a cluster, electrically speaking, because many houses have the technology, can create problems as well. So we don't need to wait until this percentage becomes much higher. We need to plan in advance because networks are being affected. So the idea here in this particular project was to really understand these clusters and how can they be managed, and also learn about, you know, how people will be using electric vehicles. For this, we gathered the information from more than 200 electric vehicle users that they needed to be part of this trial. They signed up to a lease. So it was kind of a subsidized electric vehicle. It was Nissan Leaf, all Nissan Leaf, by the way. So all the results are a little bit biased towards the technology, of course, but it's still very informative, as I will present. And the whole idea was to really, as well, trial this solution of electric vehicle charging point management. The trial had more than 100 social trials, which is just gathering the information of how people were using the car, and 100 technical trials, so 100 electric vehicles in the technical trials, which were separated in around 10 clusters where cars were actually being managed with the technology 100%. So more than 200 electric vehicles part of the trial, and all the data came to the project to assess. Now, what is this trial about? So imagine that this is the street where you live. And you have your charging points. So the idea here would be to use a little controller, like a PLC, it's a little computer, and that gets through communication infrastructure the information of whether you're actually charging or not. And it can sense as well what is happening here at the head of that particular electric feeder that is sensing all the currents, that are going through your house, or to supply the different houses. And based on some aspects, like for instance, what is the ampacity of the conductor, decides to disconnect certain cars. The question is, of course, which cars do you disconnect, or the charging points, for how long, et cetera, et cetera. So you need to come up with a control for that. The charging points were this, you can see here, this brand, Rolex here, this is a picture where, well, you have the relay, the sensors, etc. And then you have as well sensors at the head of the feeder in that little transformer that is supplying the power to all these houses. So we require control, communications, of course, infrastructure, and that is not something common in our residential electric infrastructure. So trialing this technology is very useful for the companies that manage the poles and wires. Now, the type of information that we gather from these vehicles, that these are Nissan Leaf, were provided at the time to the University of Manchester, because that's the time that I was there. And this information was coming for each of the days as the number of units that you had at each moment in time when you were about to charge or were charging, and when you were not charging. So for instance, here, what it means is that in a single day here, when you are charging, so we know that the number of units when you start and when you stop, the time, and the number of units that you stop as well, okay? And all this information from all the cars, more than 75,000 charging samples without control. And that was very useful to understand how people are using the electric vehicles. Now, some of the results, which is very interesting for modeling purposes. This information still is quite unique, despite the fact that there's more and more electric vehicles. That information is not necessarily publicly available. This information is, and well, let me share it with you. So first of all, we found out, at least here with this trial and in the considerations in the UK, that there were no significant differences in terms of the number of charging events between weekdays and weekends, and even in terms of the seasons. Okay, that's the UK. In other countries might be slightly different. Also, what we noticed is that throughout the day, there were cases where people were doing quite a number of connections, like, I don't know what you do with your phone, I guess, to some extent. But for modeling purposes, what we did was to focus on the two first connections, which really were the majority. If you add up here, 70% plus 20%, so 90% of the charging events are for 1 and 2 connections per day. So we focus on that. And what we found is that the first connection, so people that would use just 1 connection or first connection, will do it throughout the day, actually, as you can see here in this probability distribution. But there were clear peaks, if you want, during the morning. So around people when they woke up and decided to charge, or perhaps took the car, went to buy bread and milk, and then came back and then decided to charge. I don't know exactly, but that was a clear peak. And also in the evening, when you, of course, you would assume that people come back from work. And those that had a second connection definitely was at the evening. That was very, very clear here. And that's interesting because, using these probability functions, we can actually create some models. Now, in terms of the initial charging level, so when do people start charging at any point in terms of their battery state of charge, really? throughout the units. By the way, the Nissan Leaf has, instead of 0 to 100%, they showed 0 to 12 bars, 12 units, okay? So 12 units is 100% charge. Now, in terms of the final charging, that perhaps is as expected. What it really says, this graph, is that most cases, I mean, almost 70% of the cases, people charge until full. And perhaps that's as expected, I guess, you know, but it's good to know what is happening here. And all of these, what it really gave us is the opportunity to start modeling what is the average behavior of cars. Now, each car will have, of course, a different electrical behavior as a load. Imagine, you know, how we use electricity at home, but we can extract this in average. And what we found here is this blue black curve. I mean, both are models. One is the actual, and the other one is this is a model. They're not going to enter in details, but the interesting thing here is that this value goes up to, this is the average electric vehicle demand, no more than 1.2 kilowatts. Now, by the way, these cars were charging at home with the slow charging mode and the slow chargers as well, which means no more than approximately 3-point-something kilowatts. Today you can find much larger, of course, but considering that these are just houses, that is reasonable to consider as perhaps it will continue to be in the future as well for house chargers. Now, what it is important here to first say is that this 1.2 kilowatt might not seem enough. I mean, a kettle can easily be 2 kilowatts, right? However, how we designed the electricity networks, the residential electricity networks for houses in Britain, considers more or less a coincidental peak of each house of around 1.5. So having an extra 1.2 is quite a lot for those networks. So that already highlighted a potential issue. However, of course, if we have this result of an average behavior of 1.2 kilowatts, and then we put it, for instance, here in Australia, where we designed electric residential areas, the electric infrastructure for the residential areas, considering a peak because of air conditioner of around 3 kilowatts per house, then of course it is extra, but it's not necessarily significant as in Britain. So it depends as well. You know, the impact on the grid depends on where we're talking about. Anyway, that was very interesting. But now, because we have this model, we could actually now do a much more interesting impact analysis on the network, because so far it's not an impact analysis. So we modeled multiple networks that were part of this particular project. So these are the actual electricity infrastructure of those particular areas. And we also use some tools to represent how houses consume electricity. This was with a tool produced by the University of Loughborough, the CREST tool. And we use, of course, the electric vehicle profiles that we just presented, the models that we extracted from all this data that we gathered from the project. And now I'm going to show you, what will happen the moment that we see many, many cars. Because as much as we were using this trial to understand the impacts on the networks, in reality, 10 cars in a little residential area where that was designed for 50 houses, it's not an impact really. But the moment that we have 50 cars with 50 houses, then that's another story. But we didn't have that. So we did some models to understand what would happen. So the idea here, of course, is to the moment that you actually produce the models of how the electric vehicles will behave in combination with normal demand, you will see, well, that at the transformer, you will have what we call overload. So imagine your switchboard at home, you will have more currents. Of course, will exceed the limit at some point if you have too many loads. And in terms of voltages as well, and this is because of the particularities of the electricity network, because of the current. So this is basis of electric circuit, the voltage will drop. Okay, so we will do this analysis, and of course you don't want voltages to go beyond the limits of the corresponding part of the world that you are analyzing, and you don't want your assets to be overloaded. So we did this analysis for one network there. This is just a slide for one network. I mean, we did it for many networks, and this is quite a large transformer, 500 kVA, that can supply easily more than 100 houses in Britain. And usually more, actually, I think it's 300 houses we supply in this particular transformer, multiple feeders, there are 6 feeders. And what we are seeing here is that as penetration here is in the number of houses or the percentage of houses with one car, electric vehicle. So 100% means all the houses, the 300 plus houses with electric vehicles. And then, well, you have the fractions. So what we see here, although it's not very clear, is that if you follow my laser, is that at the thermal limit of the assets that we have, the feeders and transformers, are reached at around, well, 50% in this case. For the transformer, which is the transformer, which is this line here. For the feeders, meaning because we have electrical feeders like the streets, as a single transformer supplying multiple streets if you want, it's later, but the transformer, because it is aggregating all the currents, it suffers, of overload much earlier. And well, of course, depending on the type of network, the number of customers, you will have a different values, but more or less our findings shows that around 40% of penetration. So 4 in 10 houses is pretty much as you can go without having significant impacts on the electricity network, at least in Britain with the models that we have produced. When you actually really look at multiple low voltage networks, which is what we did as well in this particular project, what we found is that, yes, the transformer is the first to suffer, which is in blue at around 40% penetrations, which is 4 in 10 houses with an electric vehicle. And then, well, the feeders get congested as well as the second problem, and voltages are not necessarily a significant problem actually in this particular case. Again, this is the case of Britain, because of the characteristics of the networks, but the transformers suffer immediately because of the aggregated currents. Of course, these are cars that are not being managed. So how can we manage is the question. So that's where we present this idea here. This is called ESPRIT, the technology that EA technology patented, and we tested in this trial. And the idea is really to understand how can we, or to what extent to which we can, by managing the electric vehicle charging point, not the vehicle, the charging point, we can actually have more electric vehicles, and to what extent we affect customers, because people will have delays in their cars, well, when the time that it takes for the cars to charge. So the conceptual approach is as follows. So you disconnect the electric vehicle charging points, this VPPC here, when you have problems, and then you reconnect when there's no problem. So it looks simple, right? But the logic, the moment that you need to implement it, of course, it's not that simple. But the idea is that, the moment that you sense problems, disconnect some of the charging points. The moment that there's no problem, reconnect the charging points. So which one do you disconnect first, et cetera, et cetera. So you need to create a logic that is also fair to customers, okay? So you can use the time that they are being charged as a proxy, or different other ideas, okay? And well, the moment that you disconnect, what this little graph is showing is that this is, well, the current through the feeder, as in, one being 100%, you will, by disconnecting, and delaying the charge of some cars, then you will manage the current will not go as high as 16, the rated capacity. So that's the principle here. Now, for this particular big transformer that I mentioned earlier, that supplies to 350 customers, houses, what we're doing here is that controller with a control cycle of 1 minute, which according to Nissan Leaf at the time, they told us that, yeah, disconnecting control cycles of 1 minute or reconnecting is just way too fast. So, but these are simulations. They told us that 6 minutes would be okay. I don't know what is today really that disconnection and connection time limit. But the idea here with the simulation is just to show that, well, by following this algorithm that we propose, well, you are able to, in terms of the transformer loading, to avoid this massive peak in red that doesn't have control, that goes beyond the 500 kVA rated capacity, and then you keep it at the 500 kVA. Naturally, in this case, well, the voltage as well doesn't go as low, because of course the load is much less, but still, you sometimes have some problems with respect to the limit, which is this line here. But in general, well, you can solve the problems. So that's in principle. However, and we trialed this to some extent, as well in the actual trial, more basic algorithm. The problem is that what we are doing here as well is that we are pushing the demand coming from the electric vehicles to later, right? Because there's less normal demand, people cooking, watching telly, whatever. Later at, I don't know, midnight or whatever, and then people are sleeping, so the car starts charging at that time. Now, it is okay if you were not planning to use the car at 1 a.m. for whatever reason. But what is really happening, and this is where we need to consider the effects on customers, is that, well, a car that in red here was meant to charge, I don't know, in 2 hours and 40 minutes, in this case, this is just an example, now will take approximately 140% more, which is 6 hours and 29 minutes. Why? Because we have disconnected it, and then we're reconnecting it later on at 11 p.m. more or less. That was just an example. Of course, many other customers might not have their cars delayed, depends on many factors. But it highlights the fact that as much as technically we could mitigate the impacts on the electric grid, we need to also assess to what extent customers are going to be happy with this. In general, the trial suggests that the customers will be happy, of course, but the trial didn't consider 100% electric vehicles either. So the impact might be slightly different. So because of these impacts on customers, we created this index that's called customer impact level. It's a little bit complicated, but let me try to explain. So what we're trying to do here is that quantify how many times in percentage the additional charging time that you will have if you are part of this electric vehicle management idea. So an impact level, or CIL, of 1 means that up to 25% extra time you will require in your charging. 2 up to 50, 3 up to 75, and so on. And what these results are indicating is that, well, first of all, around half of the cars, assuming this transformer with 350 customers, so 350 cars, half of the cars are not being managed at all. Actually, they don't have delays, which is brilliant, of course. The other half, they are being managed, and well, you can argue that a good third of the cars, they require less than twice the original time. So if it was 30 minutes that you needed, now it's going to be 1 hour. If it was 1 hour, now it's 2 hours. But it depends on the cases, how long it will take in effect. But we still have, another fraction that can go quite significant. Now, having a delay of 200%, that doesn't necessarily mean that it's, multiple hours, because it depends on your original time, right? But it just shows you that, well, many customers will not necessarily be that affected, but still will be a good chunk of customers that will be affected. However, this is the 100%. The moment that you have less penetration of electric vehicles, of course, people will suffer these delays a little bit less. So just to provide a few key remarks and in terms of electric vehicle charging point management. So trials definitely are very important to capture the actual behavior of electric vehicles. And this particular project, all the reports are publicly available, really did show us interesting things. For instance, in the case of Britain, there was no seasonality effects. There were significant changes from weekday to weekend, though. And that 30%, a third of the customers, or the people using the cars, were charging more than once a day. And that was interesting as well from a modeling perspective. In the UK, based on our analysis, the impacts on the low voltage networks, so our residential circuits, they are likely to start at 40%. So the moment you have 4 in 10 houses, then you should be worried. But that might happen according to the statistics, and still in some 10 years or a little bit less. But this depends on the networks as well. In terms of electric vehicle management, well, I mean, definitely this particular trial was proving that this infrastructure works, and this is a practical solution as well. But we also need to remember that we need solutions that are cheaper and greener than traditional ones, because the option is also to upgrade the wires. And actually, the reports show as well that this has the potential, this particular technology has the potential to be cheaper and greener as well, considering certain scale of manufacturing of the corresponding elements that are needed for this. Okay, so let's move on to allocation of fast charging stations. Now, in this case, it's a different sort of problem. It's really thinking, okay, so the moment that we have people buy more electric vehicles, naturally, well, this is kind of a chicken and egg thing, you need more infrastructure that reassures people that there will be a point of connection in which they can charge their batteries. However, the moment that you really look at this particular problem of fast charging stations, like petrol stations, is very, very similar. You need to consider traffic aspects. You will not ever see a petrol station that is in a place where no car passes by. All right. And understanding traffic is very complex as well. It depends on the population, the city, and the behavior of customers because of the drivers because of different reasons. Not only that, also we need to consider the fact that depending on where these fast charging stations are, you will kind of push EV drivers to follow certain routes as well, just to use them if they need to. I mean, in addition to their charging at home, of course. And that can create some challenges as well, because it means that you might concentrate certain areas with these fast charging stations, and that can create some effects on traffic as well. Or if not effects on traffic, as in saying, now we have huge traffic in certain areas. It's not that. It might create inefficiencies, loss of productivity, people traveling a little bit more just because of the fast charging station or diverting themselves. So you want to have well-located fast charging stations based on the traffic as well. You want also to consider the impacts on the corresponding electricity grid, not longer the residential areas, but the larger pylons, the larger conductors and transformers as well. And it all depends, of course, on how people are using these charging stations and the corresponding reforms that are needed, and how big these charging stations are as well. Because when we talk about fast charging stations, it's not just one that can easily take 50 kilowatts of power, but it can be multiple of them, 10 of them. Again, similar to a petrol station, you have more than one pump. So same thing here. And that is a big load, all right, electrically speaking. And of course, you have the economic layer, because the location means land, means equipment, because of the corresponding charging stations that you require and the corresponding impact on electricity. So all of this is interrelated. And at the end of the day, you need to do this per city or per regional area. And then therefore, because you have the commuting aspects of multiple cities, this needs to be geo-referenced. And this is quite a complex task. So we need adequate fast charging location, but also this needs to combine all these layers. And well, I mean, this is quite challenging. So in the next slides, I will present the results of an interesting PhD project that we did in collaboration with the University of Campinas in Brazil. Now, given that these guys in the University of Campinas have also access to the electricity network, we modeled the corresponding roads as well, so as to create models for the different layers that I just explained in the previous slide. So, well, what you have here is a map of Campinas, the city, and then the different cities that are around it. So the idea was to really model the traffic flows, modeling the roads as well, not just the electric network that is actually modeled as well by the corresponding company there, and also was given to the University of Campinas to carry out research. So we actually had to model all the different aspects. So we consider just the central city, not all the cities here in the Campinas metro region. We needed to model the cars, but of course, this modeling is always such a large scale, which we're talking about millions of cars, then it's quite complex. So what we did is a reduced model of just 1% of the total registered cars, which is like 8,000 agents, which is cars for the traffic model. We consider 50% electric vehicle penetration, and we consider as well travel cost to sort of as a proxy of the loss of productivity. Well, not proxy, it's actually the direct measure of the loss of productivity because of traffic. So if you lose time in your car because of traffic, diverted, or just traffic is slow, then that's a cost, a societal cost, not a cost to you necessarily, but a cost to society because you are being inefficient. So we considered different costs in Brazilian reais, which is approximately, well, 2, 5, and 7 American dollars as of today exchange. We consider, of course, as I mentioned, the electric grid for that corresponding area, which is a significant modeling task. And of course, the economic aspects of, fast charging stations, their costs, reinforcement costs, land costs, etc., etc., etc. And what we were considering in this particular case studies, up to 20 fast charging station locations, where each of the charging stations, the chargers, if you want, is 50 kilowatts each. So a single fast charging station, when we talk about fast charging station location, is really, well, what you can have multiple of them, all right? So if you say 10, well, suddenly, well, we have 500 kilowatts of total demand, right? But all these 10 can be in one place, like multiple pumps in a petrol station. All right, so more details are in this particular paper, but let's go on with the results here. So I'm not going to go into the details of the methodology. The idea is to really give you a glimpse of what can be done and what is needed perhaps for the future. So the moment that you have this traffic model, then we can actually run a simulation saying, well, no electric vehicles, how people are using these cars, all right, in this particular region. And what you very quickly can spot is that here in bold are the roads, right, and the avenues that are highly utilized because of commuting, because of the different needs of this particular region in Brazil. And very quickly, what you can say is like, okay, so let's pick the most utilized roads by the vehicles, and let's select them as the best candidates for fast charging station places, all right? So again, nothing too far from what a petrol station investor would do, all right? Because it makes sense. That's what you want. It's efficient for everyone, you know. But still, you know, the question is this really the best or not? So we selected these 20 locations to study them. And the first study that we did here, and then there are multiple aspects. The first one is the travel cost, or what I would call loss of productivity. So different sensitivities, sabermetrics here, then Brazilian reais per hour, 25 and 40, we have that, you know, with more charging stations, now considering 50% of vehicles now become electric vehicles, the more you have, the more you diversify the fast charging stations, the less loss of productivity. Why? Because, of course, people don't have to travel big distances just to use the fast charging station. They are still charging at home. We quantify that, but still, that diversity definitely helps reducing traffic, and then therefore that diversity reduces the corresponding travel cost. We did this with Monte Carlo simulations, so that's why you have here the box plots, but we're presenting the median values as well, just to simplify all the plots. So the more fast charging stations, the more diversity you have, less traffic, and the more productivity. But what happens with other aspects of installing, of allocating fast charging stations? So here we have land cost, the fast charging station cost, the actual cost of the station, transformer cost, which is the transformer that is required for that fast charging stations, like creating a building. If it's a big one, then you will need not just to build the building and the corresponding things that go inside the building, but the transformer as well that connects to the electrical network. And then there are the reinforcement costs. So these are the electrical things that need to be upgraded around you because of the extra load that you are bringing. In this case, what we are seeing is that in terms of land, well, the more diversity that you have, the more stations that you have across this metropolitan region, well, the cost starts flattening. So it's not that it just goes up and up and up. Why is this? This is because it means that when we talk about a fast charging station, you have less chargers per station, but in more locations. So instead of creating a massive one with 10, 20 chargers, because it's the only one in the whole city, then now you have multiple ones with less chargers each. So less use of land per location, particularly with the closer they get to the city center, the more expensive. And then that diversity helps flattening the land cost in total. In terms of the corresponding fast charging station cost, well, I mean, the more charges you have, the more assets, and then therefore the more cost that goes up naturally. And the more transformers, the more assets you have, the more transformers as well. So that goes as well up and up in this case. Now, in terms of reinforcements of the electricity network associated to these locations, then this is interesting. In this case, what you create is the more diversity, the less impacts on the corresponding parts of the electric network, which is interesting. So diversity is definitely good. Concentration of fast charging stations is definitely not good. Now, the moment that you combine all of these, what you find is the cost associated to all these aspects that I'm just mentioning. And what we find is that, well, yes, then the fewer the fast charging stations, reduces capital cost, of course, but then increases indirect cost, which means, land and, for instance, the travel time, because people have to travel to these places. And that is just very inefficient. Of course, this also changes depending on the corresponding travel cost, the loss of productivity cost that you will use. But in general, what we're seeing here is that, well, around 2 fast charging stations with multiple charges, of course, or 9 might be the optimal. Definitely, if loss of productivity is a concern, well, 9 will be the best solution for this particular regional city. And if you want to see what are these 9 points, well, these are the 9 points that are selected. I'm not going to go through the details of the areas and the number of charging points that you have in each of the corresponding stations. You can see here that are quite a number. Some of them are massive, actually, as a matter of fact. But what you see here with this table that presents the capital indirect cost, the most important thing is that, you know, the capital cost and the traffic are the main cost components. So as much as I was saying initially, the electrical aspect needs to be considered, and it needs to be considered, clearly it is really the traffic. I mean, if we look at smart cities, if we look at the future of cities, yes, we need to look at the cost of the electrical grid, you know, because of the impacts of having more load. But clearly what we need to really model properly as well are the traffic flows and the cost to society of having inefficient traffic flows. Of course, the cost of the actual chargers, the land associated with each fast charging station, that's really a big part of the whole thing. And this will be done by investor, of course. But I mean, what we're quantifying here is a whole, just to understand the societal cost of this infrastructure. But for you to come up with these conclusions, you need to do this modeling that actually addresses all these aspects simultaneously. Now, just to conclude this second part and really to finalize my presentation, that I hope that you have enjoyed. Here are just a few key remarks. Future cities or future smart cities, they will need to consider holistically the location of fast charging stations. So traffic flows, EV infrastructure, and electric networks, they all have to model simultaneously. So it's not just infrastructure costs. We need to understand societal costs as well. Modeling approaches to do this need to be scalable. These are massive pieces of data, the traffic flows and the electrical networks. It's not possible really to carry out typical optimization techniques. This is brute force analysis that needs to be carried out. I mean, Monte Carlo simulations, et cetera, et cetera. And this needs to be done in a time varying way. So we need the time component as well to really understand what is happening, which is making the whole process much more challenging. And data is of course a challenge. It's not just about electric vehicle behavior, charging behavior, but geo-reference data, you know, to do this modeling is very important. And this comes from different stakeholders, you know, cities, transport sector, and of course the electrical network, and that is challenging to put together. Well, there's further reading. I will provide the slides here that doesn't include questions, anything, so for you, and as well electric vehicles in Latin America. And of course, on my website, there's more information on our available papers and reports as well. There are some seminars as well in the IEEE PS Resource Center and IEEE Smart Grid Resource Center, and more than happy to answer your questions. But before saying bye, I would like to acknowledge Dr. Jairo Quiroz from the University of Costa Rica, EA Technology. Both were partners in the project of My Electric Avenue, and Juninho Andrade from the University of Campinas, and Valmir Freitas from Unicamp, Brazil, Professor Valmir Freitas, actually, as a matter of fact, that were collaborators, of course, in the project with Unicamp. And well, again, thank the conference for this kind invitation. I'm more than happy to answer your questions. Of course, thanks to the University of Melbourne and the University of Manchester. That is my email for any questions, and I will be online, of course, live to answer your questions during the conference. Thank you very much. Bye-bye.